morning, I'm Taylor.
I'm Josh.
I'm Boy.
And I'm Ryan.
And we're going to be talking about the characteristics and elements of communication systems. An important thing to remember when looking at a transmission system is that when you send a signal, whether it's analog or digital, is that it can be corrupted at any time. This corruption of a signal is known as a transmission impairment. Transmission impairments result from noise, attenuation, and distortion. Attenuation is the most simple topic of transmission impairment. All it means is that when you send a signal across a transmission line, it loses its strength over that line. Attenuation increases when frequency is increased, and it also increases when the distance is increased. The diagram on the slide shows a simple figure of how attenuation is affected as a signal goes across a certain distance at a certain time. Noise is a random variation of an electrical signal. In 1918, Walter Schottky found two major sources of noise in digital communication. One is thermal. Thermal noise happens when applied voltage goes on a semiconductor or a conductor, and when that happens, the temperature increases on the transmission line. Shot noise is random fluctuation of electrical current. This is caused by floating electrons bouncing off of each other. So thermal depends on applied voltage, and shot noise depends on current. Noise in a system will disturb the system's performance. The more noise there is, the worse it does. One important aspect to look at when looking at noise is the signal-to-noise ratio, or SNR. When determining the performance of the receiver, SNR is good to look at. On the slide, it says the formula, and it's measured in decibels. SNR is equal to 10 log base 10 of the signal power over the noise power.
So the next type of transmission impairment that we'll be talking about is distortion. Distortion is any change from the original signal or waveform that is passed through from the transmitter to the receiver or through transmission lines. There are different types of distortions. There's amplitude distortion, frequency distortion, phase distortion, harmonic distortion, and they all occur in different circuits or when you pass them through different filters or even transmission lines. In the example here, we have a linear waveform, one showing a square and a sine wave, and we can see the different types of distortions that occur when it is passed through different types of filters or when we manipulate the waveform. In the first example, we see a high-pass filter, and in the second example, we see a low-pass filter. In the third example, we see an irregular waveform, and then in the last example, we see one that causes the waveform to create clipping in the signal that is being transmitted across. So there are different types of distortion possibilities that can occur in in waveforms and signals, but the one we'll be focusing on today is frequency delay distortion. So as we said, distortion is a change or alteration of the original signal transmission. In this case here, we have a signal that is being transmitted through a transmission line. As it goes through the transmission line, we can see that it has become distorted into a different figure. This occurs because many frequencies will be passing through the transmission line, which will alter the waveform as it is received through the receiver. This is because of propagation velocity, and it is directly related to the frequency. And when this happens, we can get different types of waveforms that occur. And as engineers, we don't like that to happen because when we are receiving signals, we want it to be as clear as when we are sending out those signals.
In digital communications, we call time delay distortion intersymbol interference, where the signal is received multiple times over a period and the ones and zeros of the signal can overlap each other. It is important to reduce intersymbol interference in every piece of your system to have the smallest error rate possible at the end. One way to show intersymbol interference graphically is through the use of an eye diagram, where an oscilloscope measures time samples and amplitude of your digital signal and shows it on the graph. The farther the amplitude is from 0 at the measurement points, the cleaner you have the signal coming in. Here we see the eye halfway closed, where there's a lot of intersymbol interference and a lot of noise along with it. We see the effects of intersymbol interference most in urban environments, where cell phone signals can bounce around many times before reaching their destination. What happens is the receiver gets all these signals, sums them up, and sees many ones and zeros on top of each other. In an urban environment, it could take up to 10 microseconds before the signal is finished being received. The way we alleviate this is to increase the sampling period. Here we see 4 symbols coming in, and on the second symbol, the first one is still part of the sample, so it's overlapping. If we just increase the period, we can finish with symbol 1 and then move on to receiving symbol 2.
To reduce noise, attenuation, and distortion, we can increase or alter the channel capacity. So when transmitting data, it is important to send information quickly without being corrupted. But to do that, there are a few key aspects that we have to take into consideration, such as the bandwidth of the channel and the noise produced within the channel. We prefer that the channel be noise-free, but in some cases the channel can be very noisy. According to Harry Nyquist, the pulse rate has to be equal or less than twice the bandwidth. So as we can see here, FP is less than or equal to 2 times the bandwidth. It was also found that the maximum number of distinct pulses that can be sent over a channel is limited to the dynamic range of the signal's amplitude. So in the past, it was this problem because when the data was sent too quickly or too close together, the data can bleed over itself and it would corrupt the data. It is also affected by the receiver's ability to distinguish the amplitude levels, otherwise known as the receiver's resolution. Based on that, the maximum data rate is here, FB equal to FP log base 2 of M, where M is the number of distinct pulses. But if we wanted to calculate the maximum data rate in a noise-free channel, the equation is altered. FB is less than or equal to 2 times the bandwidth times log base 2 of M, where M is the number of distinct pulses. Combining all of those, a new theorem was evolved, which stated that the maximum data that can be transmitted over a channel that is affected by extra white Gaussian noise is the channel capacity, where it is equal to 3.322 times bandwidth times log base 10 of 1 plus signal to noise ratio. Or it's also channel capacity is equal to bandwidth log base 2 of 1 plus signal to noise ratio.